Chapter 3 introduces the idea of the derivative. It starts with the definitions of the derivative using the limit process, and then it continues introducing some basic rules and some differentiations rules that we can use in order to find the derivative of any functions. Let's start with a graph. So I graph the functions x squared plus 4x is a parabola. And I look at this point when x equals to 1 and y equals to 5. Right? My goal is I want to find the slope of the tangent line that goes through this point right here. And then if you remember what we learned on the very first day, in order to estimate the slope of the tangent line, we use secant line. In order to use secant lines, we need to pick a point. So I pick a random point here. X equals to -2 and y equals to -4. All right. And as you can see that the distance between, not the distance, but the distance between the two x values of these two values is h. So h tells you the difference between the x values of the first point and the distance between the x value of the first point and the x values of the second point, which is h. And in our lectures, we use delta x replaced for h here. So delta x is just the difference between these two x-axes. All right, so now I want to graph a secant line that goes through these 2 points. This blue line here is a secant line that goes through the point 1, 5 and -2, -4. And then as we decrease the distance of h, we will get a better estimations for the slope of the tangent line that goes through this point. So I will drag the point h closer and closer and closer and closer and closer to the point x equals to 1. As you can see that the point is moving, right? H is decreasing. And this process is called the limit process. When you decrease the difference between the two x values of the 2 points in order to estimate the slope of the tangent line that goes through this point right here. And as this points go closer and closer and closer and closer to the point C, we will get a very, very good estimation for the slope of the tangent line that goes through 1. All right, and we can look at the real tangent line that goes through 1, which is the black line. So the black lines here is the tangent line that goes through this point. And the blue line is the secant line that using the second point to estimate the black line. And you can see that when h decreasing and it goes to 0, we have a good estimations of the slope of the tangent line. In fact, using this limit process, as h goes to h decreasing down to a very small number that is very close to 0, you will get the slope of the tangent line of a functions at a point. All right, so here is the definitions of the slope of the tangent line with the slope m. As you can see that you're using the limit process when you have limits of delta x, and again, delta x is h here, is the distance between the two x values. When delta x goes to 0, the secant lines of the 2 points will approach to m, which is the slope of the secant line that goes through the point C and f of C. Now, if we want to look at the first example, we have a functions f of x equals to 3 minus 5 of x here. And we want to find the slope of the tangent line at this given point when -1 is c and 8 is f of c. Okay, using the definitions, we want to use the limit process when delta x goes to 0. And you plug f of c plus delta x. Again, delta x now is a variable, and c is -1. And you plug c plus delta x into these functions, you will get 3 minus 5. C is -1 plus delta x is a variable, and minus f of c, which is 8. And everything divided by delta x. And at this point, it turns to a limit problem when you cannot plug 0 into delta x just now, right? You cannot do that. So you have to somehow using algebra to find this limit. And the first thing that came to my mind can be, I can try to simplify the numerator by distribute this in here. -5 times -1 is +5, and then minus 5 delta x minus 8 divided by delta x. And you can see that we can, so 3 plus 5, 8 minus 8 is 0. So what left over is -5 delta x over delta x. And then you can cancel the delta x, which gives you the solutions of -5. All right, so you can say that the slope of the tangent line of the functions 3 minus 5x when x equals to -1 is -5. Go to the next problem. Again, we identify this is c and this is f of c. Okay, and then we use the limit process. Again, so you want to see take the delta x go to 0 of f of c plus delta x. So c plus delta x, where c is 1, so I have 1 plus delta x. I should use delta t, right? Because the variable now is t. So you should use t here instead of x. One plus delta t squared plus 4 times 1 plus delta t. Okay, so this is f of 1 plus delta t minus f of c, which is 5. Everything divided by delta t. And again, we cannot plug 0 into delta t, so we have to use algebra. I'm just gonna simplify the numerator. So before I can simplify it, I want to distribute everything out. So 1 plus delta t squared is 1 squared plus delta t squared plus 2 times 1 times delta t, so 2 delta t, plus 4 plus 4 delta t minus 5 divided by delta t. Okay, and then at this point, you can see what can you cancel right now. You can cancel 1 plus 4 is 5, minus 5 is gone. So what left over is t divided 0, delta t squared plus 2 delta t plus 4 delta t is 6 delta t divided by delta t. And then you see that you have delta t in every single term here. That means you can cancel one term of the delta t. So I cancel this delta t, cancel this delta t. Two terms, I cancel it, so it's not 1. So the left over after this step is delta t plus 6. Now you can ask yourself, can I plug 0 into delta t? And the answer is yes, right? Because it's not going to give us any problem. So the answer for this problem, for this question is 6. It should be the answer. So 6 is the slope of the tangent line that goes through this point of these functions. Now that we just talked about how to find the slope of the tangent line at a given point, and then if you ask for a slope, you will have to give a number, right, of values. But in case that people just want us to find the slope of the tangent lines at any point for any given functions, how can we find that slope? And if you have a function that is continuous change, then the slope of the functions change as you go through a different point, right? If you have a slopes of the functions that is changed as you go through different points, then the slopes is defined by a functions. So what is the definitions of the derivative of the functions? It's very similar to how we define the slope of the tangent line at a given point. So the derivative of the functions f at x is denoted by f prime of x equals to the limit of delta x goes to 0 of f of x plus delta x minus f of x divided by delta x. And again, at this point, we have x as a variable, and delta x is the variable where we're taking the limit of, and x is the variable of the functions that we're looking at. All right. So for all x for which this limit exists, f prime is a function of x. Again, if you want to find the derivative of the functions, then you give a functions in terms of x. It's not a value, it's not a real number, it has to be a functions. Okay, so the derivative is the instantaneous rate of change of one variable with respect to another one. For an example, if you're talking about the functions f of x, then the derivative f prime of x is the instantaneous rate of change of the variable f of x in terms of x. So x is the input and f of x is the output. Sometimes people use y, right? You use y instead of f of x, or you either use f of x instead of y. And then the process of finding the derivative is called differentiation. Finding the derivative is the differentiations is the derivative of the function. And then a function is differentiable at x when its derivative exists at x, and it's differentiable on an open interval a to b when it is differentiable at every single point on the interval. All right, so if the derivative exists, if the limits here exist, then the function is differentiable at x. If the limits here exist on an open interval, then the functions is differentiable on the whole interval from a to b. There is different notations for the derivatives. So again, sometimes people use f of x as the output, right? Or they use y as the output. So if f of x is the output, that means x has to be the input. All right, so you can use f prime of x to denote the derivative of f of x. You can use dy over dx to denote the derivative of y, of the functions y in terms of x. So dx here will tell you the input of the functions. Or you can use d over dx of f of x. Again, it's just the derivative of f of x in terms of x. Or you can use big D, x and y in the brackets. Again, it denotes the derivative of y in terms of x. So again, the derivative of the functions is the instantaneous change of one variable over another variable. And if you look at the limits definition, the limits process here, it's a change of the y variables over the change of the x variable. That's what it is. And it's instantaneous changing. It's not a static change. It's continuous changing. All right, that's the idea of the derivative of a functions. And you're going to use limit process to find the derivative of any functions. All right, let's look at the first example. If you're given this parabola, if you want to find the derivative of these functions by using by the limit process, how can you do that? You can use the definitions of the derivative, which is this limit definitions here. So I want to write out the limit process, the definitions of the derivative. So f prime of x, I use f prime of x equals to the limit of delta x, which is the difference of x, of f of x plus delta x minus f of x, which is the difference of y, right, of the 2 points divided by delta x, which is the difference of the 2 x's. And in this case, I always have my lim delta x goes to 0, indicates that I'm doing a limit process problem. And then I'm gonna plug x plus delta x into my functions f of x. So x plus delta x, so it is the input. So you just need to replace x plus delta x, okay? You square it because it's x squared plus 1 minus f of x. Sorry, it's not c, it should be x. So minus f of x. So what is f of x? F of x is actually this function's f of x, x squared plus 1. And everything over delta x. Again, this is f of x plus delta x. And this is f of x. And this is delta x. All right. Now, again, this is a limit problem. I just need to use my skill of finding limits that I learned in chapter 2 to find this limit. Limit delta x goes to 0. Again, you cannot plug 0 into delta x because it's in the denominator. So we have to simplify the numerator. First, I want to distribute the x plus delta x squared. So it's x squared plus 2x times delta x plus delta x squared plus 1, right? Minus, remember I have the minus in front of the parenthesis. I have to apply it to each term inside the parenthesis. So minus and minus delta x. What I have next is, let's see, what can I cancel? X squared, 1, negative 1, right? What left over is 2x times delta x plus delta x squared over delta x. And you can see that I have delta x in every single term. That means I can cancel one of the delta x term. So I cancel this, cancel this, cancel this, right? And what left over is 2 times x plus delta x. I cancel one term, I still have another term, and delta x divided by delta x is 1. All right, now can I plug 0 into delta x? The answer is yes, because delta x is not in the denominator anymore. So my answer is, if I plug 0 into x, I have 2x plus 0 over 1, and the answer is 2x. All right, let's go to the next question. Again, I want to find the derivative of these functions, and this is the rational functions. Let's write down the definitions of the derivative. F prime of x equals to limits of delta x go to 0 of f of x plus delta x minus f of x over delta x, okay, equals to limit of delta x goes to 0. I plug x plus delta x into my functions to get, I'm using another color. So 2 over 4, instead of x, I replace x plus delta x minus 3, right? And then minus f of x is just 2 over 4x minus 3, and everything divided by delta x. All right, again, here is my, this is my f of x plus delta x, and this is my f of x by the definitions. All right. So now I cannot plug it in, right? So I have to simplify the numerator. Minus 0. I want to combine the two fractions together by finding the most common denominator. The common denominator has to be the products of the two denominator because they're not sharing any common term. So common denominator is 4x plus delta x minus 3 is the first denominator, multiplied to 4x minus 3, okay? And then the top is gonna be 2 times 4x minus 3 minus 2 times 4x plus delta x minus 3. I want to have a bracket here. And everything I want to divide it by delta x. If you're wondering, how can I come up with this numerator? I use the cross multiplications rule. You multiply this 2 times 4x minus 3, and then you minus this 2 times this denominator. And then you want to put it in a bracket just to make sure that you're separating this denominator and this 2. All right. The next step is I want to combine. So you have one fractions. You have one fraction in the top divided by delta x. I want to combine it. Equals to, I will combine it, and by bringing this delta x up to this denominator. If you remember the rule that we talked earlier in the course, if you have a divided by, so this is a hard color to see. A divided by b, right? And r over c is the same as a divided by b times c. So this is the rule that I'm going to use. So I'm going to bring the delta x up to this denominator. And at the same time, I will distribute the numerator out in order to simplify it. So let's see. Limit delta x goes to 0. I have 8x minus 6, right? Minus, I put in parentheses just to make sure, minus 2 times 4x, which is 8x, minus 2 times delta x with negative 2 delta x, minus 2 minus 3 is plus 6, divided by, I keep the denominator the same, and I bring the delta x up here. All right, see what I can, how can I simplify something in the numerator? So I have negative 6 and positive 6 is gone. Positive 8, negative 8, so it's gone. So the only left over is negative 2 delta x. Okay, I want to put it up here. Let's go down here. So I have limit delta x goes to 0 of -2 delta x over 4, again I rewrite it, plus delta x minus 3, 4x minus 3, and delta x. Okay, and at this point I can cancel my delta x. Ooh, great. All right, and then I ask myself, can I plug 0 into delta x? And the answer is yes, because it's not gonna give, it's not gonna make the denominator equal to 0. So I go ahead and plug 0 in to finish my problem. If I plug the 0 in, I will finishing the limit process, limits problem. So then the answer is -2 over 4 x plus 0, right? Minus 3 and 4x minus 3. And x plus 0 is just x, so it's going to be -2. 4x minus 3 times 4x minus 3 should be 4x minus 3 squared. And then this is my answer. All right. This is an example of how to find the derivative of irrational functions. How about if you have a radical functions? Again, finding the derivative using the limit process is using these definitions. And again, I'm gonna plug f of x plus delta x using a different color. Let's see, so the square root of 2. Instead of x, I plug x plus delta x plus 1 minus f of x is square root of 2x plus 1 over delta x. Okay, and again, I cannot plug 0 into the delta x, so I have to do something with my functions. I have to use algebra to manipulate it. Again, we have it at this point, we have a radical, 2 radicals here. We should think of multiply these functions by the conjugate of these 2 radicals, right? So the conjugate terms is very similar to this term, but you still have the first functions here divided by delta x, and you multiply the top by the conjugate term. So you see it's very similar, x plus 1, but this has a plus instead of the minus here, 2x plus 1. And if you multiply something to the top, you have to multiply the same thing to the bottom, 2x plus 1. All right. And then at this point, see what we can do. We can, when we take this multiplied to its conjugate term, it will help canceling out the radicals. So that will give us, we still have limits here. Yeah, so this term square, right? Minus the second term square over the same denominator. Okay, and once you square it, you get rid of the radical. So you will have just 2x plus delta x plus 1 minus 2x plus 1. Remember, you want to put in the parenthesis here over the same denominator. All right, let's see what we have here. So now at this point, we can simplify the numerator a little bit, right? You have 2x minus 2x, you have 2, you have 1 minus 1, and the only leftover is 2 delta x. So let me write it down. Make sure that you see it clearly. You have 2x plus 2 delta x plus 1 minus 2x minus 1 over the same denominator. This cancel this out, right? And 1 cancel the 1. Left over is, and then now you have delta x, cancel the delta x. So what left over is 2 over square root of 2x plus delta x plus 1 plus 2x plus 1. And then you can ask yourself, can I plug 0 into the delta x to find the limit? Yes, because it's not going to make the denominator equal to 0. So our answer should be 0 in here. I have to go over this a little bit. Let's go here. This goes 2. Use a different color. Two over square root of x plus 0 is just 0. So 2x plus 1, okay, plus square root of 2x plus 1. And if you want to combine it, it's going to be 2 over 2 square root of 2x plus 1. And it's going to be just 1 over square root of 2x plus 1 is your answer. Next, we're going to discuss the relation between differentiability and continuity. So there are some functions that are not differentiable at some particular point. For an example, even though the function is continuous at that point, but it's still not differentiable in some special points. All right, first, when you have functions whose graph has a short term like this function, absolute value functions. At the point x equals to 1, the function's f of x is not differentiable. So you can see because it's a short term, right? You have no idea what is the tangent line, the slope of the tangent line at the point x equals to 1. So f prime of 1 is not defined, even though f of 1 is continuous. Oh, it's not differentiable, I'm sorry. Oh yeah, right. So f prime of 1 is not defined, which means the function f of x when x equals 1 is not differentiable at x equals to 1, even though at f of 1 is defined and continuous. All right, at this point, x equals to 1. The second function is the function whose graph has a vertical tangent line when x equals to 0. At this point, x equals to 0, if you draw a tangent line, it will give you a vertical tangent line. And the slope of the vertical line is undefined. So that's why f prime of 0 is undefined. Even though f, as you can, in other words, like f of x is not differentiable at x equals to 0. Even though f of 0 is defined and continuous. All right, and the last functions is this is one of the special functions when the graph is wiggling too much around x equals to 0 again. So the function is not differentiable when x equals to 0. At x equals to 0. You know the limits does exist, right? And then f of 0 in this case is not defined. And discontinuous. All right, okay. So here's the three special examples when a function is not differentiable at some special point. When you have a sharp turn, when you have a vertical tangent line, or when your graph is wiggling too much around that point. And we can come up with a theorem, say, this theorem says the differentiability implies continuities. That means if a function is differentiable at a point, it implies that the function is continuous at the same point. So if f of x is differentiable when x equals to c, it implies that f of x implies that f is continuous when x equals to c. And the converse is not true. You can see the examples above here, right? Even though the function is continuous at some point, but in some cases it's not differentiable. So this lecture introduces some ideas on what is the derivative and how can you find the derivative using limit process. And we finished the lectures talking about the relation between the differentiations and the continuity of a function at some special point.